Before we get started on this lesson, go ahead and check the warm-up. And what you're doing is you are looking at these two pictures and trying to come up with a good definition for a central angle, and then these two pictures and trying to come up with a good definition of an inscribed angle. You'll see that this picture right here tells you that what central angles are, and this one tells you what central angles are not. Same thing over here. Inscribed angles, not inscribed angles. So go ahead and take a look at those and see if you can come up with a good definition for each of those words, and then unpause the video and we will go over it. So if you take a look at central angles, you'll see that the three angles that they list over here, all of the vertex of all those angles is at the center of the circle. Whereas if you look over here, PQR, PQS, and etc., the vertex of those angles are not at the center of the circle. So a good definition of a central angle is an angle that has its vertex at the center of the circle. Okay. Now, if you come over here to an inscribed angle, you'll see that it's a little bit different. You have AEC, you have CDE, ECD. The vertex of those angles are on the outside of the circle. And if you look at the other ones, you'll see that the vertex of these angles are either outside the circle or on the center of the circle. So one thing that you'll notice is the inscribed angles are all on the inside of the circle. So they are angles where the vertex is on the circle and its sides are chords. Okay. So what we're going to do in this lesson is, unlike the last lesson where we explored the properties of tangent lines, a line that intersects the circle only once, in this lesson we're going to investigate the properties of chords, which is a line segment whose endpoints lie on the circle. So it intersects the circle twice. So the first thing that we're going to explore is we are going to explore the relationship between chords and their central angles. So what we're going to do, and you can follow along with us on Desmos, is go to desmos.com/geometry, and we're going to construct a large circle. We're going to label the center O, and we're going to construct two congruent chords in your circle. Label the chords A, B, and C, D. So come over here, and I'm going to delete a lot of this stuff that I already had. Let's delete it all. So we're going to create a circle. Label the middle O. And then we are going to create two chords that are congruent. Go here, and what we'll do to make sure that they're congruent, we will cheat just a little bit. We'll label them, and then we'll come over here. I'll go there, and we're going to adjust these if their lengths are not the same. So currently they are not, so we need 6.1. There we go. So we have two chords that are congruent to each other. It then said to label the chords A, B, and C, D. So we'll label this A, B, C, and D. And after that it said construct the radii OA, OB, OC, and OD. So it means draw our radii from OA, OB, OC, and OD. Now, the first thing that we're going to do is we are going to measure angle BOA and angle DOC. So if we want to measure those, we have BOA and we have DOC. And you should notice, if you take a look at those two angles, you'll notice that they are congruent. So what that allows us to say is that if we have two chords in a circle that are congruent, then they create two central angles that are congruent. Okay, so again, if your chords are congruent, if you look at this picture right here, that means that your central angles are also going to be congruent. Now, next thing we're going to take a look at says, if we know that these two central angles are congruent, what can we say about these intercepted arcs right here? So if we look at this, from here to here, from here to here, what can we say about these distances? Well, recall that we know that the intercepted arcs have the same measurement as the central angles. So if these two central angles are congruent, that would mean that these intercepted arcs are congruent. So we know that if two chords in a circle are congruent, then their intercepted arcs are congruent. So if we were to jump back over to Desmos, we see that these two chords, AB and CD, are congruent. That means we know the arc AB is congruent to the arc CD, and we know that both of them are equal to 93 degrees. So now we're going to take a look at the relationship between the chords and the center of the circle. So again, this time it says, on Desmos, construct a large circle and mark the center. So let's construct a circle. We'll mark the center. Move this so that's not up against the side of the screen. We'll mark this center. We'll just call it A. And then it says to construct two non-parallel congruent chords. Actually, let's go back here and use this one since we already have our congruent chords here. And so what it says to do is construct two non-parallel congruent chords, then construct the perpendiculars from the center to each chord. So we want a perpendicular line that goes from the center to this chord. So Desmos allows us to create a perpendicular line. We want to create a perpendicular line that is perpendicular to here and passes through the center, and then perpendicular to this one and passes through the center. And let me adjust this so it's a little less muddled. So we want that line segment and that line segment. And so if we get rid of this line, we'll hide that, and we'll hide this. We have those two segments right there, those perpendicular segments. And what it asks then is, how does the perpendicular from the center of a circle to a chord divide the chord? Meaning, how does this segment, call this E, and we'll call this F, how does OE divide AB? So if we look at this, we want to measure the length of this segment and this segment right here. So we measure it, label that 3.05, 3.05. We also want to measure this segment over here, CF and FD. So label, and we'll hide that label right there. So you'll see that the perpendicular line the perpendicular line to AB from the center of the circle bisects that chord. So if we come over here, we see that the perpendicular from the center of a circle to a chord is the bisector of the chord. So again, we know that these chords are bisected by the perpendicular line. Now, The next thing it says, continue this investigation, is we want to compare the distance measured along the perpendicular from the center to the chords. So what does that mean? That means what is this distance from O? What is the distance of OE and OF? So if we look at this, we'll measure that real quick. We'll see that the distance from OE to OF is the same. So what that allows us to say is that if we have two congruent chords in a circle, they are equidistant from the center of the circle. So if we go back up to this picture, what does that mean? That means that this distance right here is congruent to this distance. Now, the last thing that we're going to take a look at is what do we notice about the perpendicular bisector of a chord? So for the perpendicular bisector of a chord, we're going to create another circle, and then we're going to create two non-parallel chords. There we go. And then we are going to construct the perpendicular bisector of each chord. So to construct a perpendicular bisector, we would need to know the midpoint of this chord, and then we would need to create a perpendicular line from to this line or that chord through the midpoint, and same thing over here, perpendicular to this chord passes through that midpoint. And the question is, well, what do you notice about the point of intersection? And you should notice that they intersect in the center of the circle. So the perpendicular bisector of a chord passes through the center of the circle. So what that means is if you draw a chord and you find the perpendicular bisector of that chord, then you can find the center of any circle. And therefore you can find the vertex of, that's interesting, the vertex of the central angle to any arc. So all you have to do in order to find the center of any circle is construct two non-parallel chords and find out where they intersect. So we're going to do one real quick proof of these chords and central angles conjecture, meaning we want to show that the central angles are congruent to each other. So what we have here is a flowchart proof. We are given circle O, and we know that there are chords A, B, and CD. So AB is congruent to CD. We want to show that angle AOB is congruent to angle COD. So AB is congruent to CD, we're given that. And then BO is congruent to DO. So we're saying BO is congruent to DO. And we know that because all radii, they're both radii of that circle, so all radii of a circle are congruent. That is the same thing with AO and CO. We know AO is congruent to CO. Well, if you look at that, we now know triangle, we have triangle OAB is congruent to triangle OCD. And we know that because of the side-side-side congruency conjecture. So since those two triangles are congruent, that means that we know all the corresponding angles are congruent. So that means angle AOB is congruent to angle COD by corresponding parts of congruent triangles. So the last few things we're going to look at this question to summarize what we've talked about, and then look at two examples. The summary question says, congruent chords are equidistant from the center. can we say anything about the distance from the center if one chord is longer than the other? And the answer is yes. So longer chords are are closer to the center of a circle than shorter chords. Now, some examples of problems that we're going to take a look at are these two right here. So it tells us AB is equal to 14 centimeters. So we know AB is equal to 14 centimeters. We also know that angle or arc AB is 110 degrees. That's 110 degrees. And what we want to know is we want to know the measure of angle CAD and we want to know what dB is, the length of dB. Okay, so we know that what we have here is we have a perpendicular line to this chord, or right here. So we know that this distance right here from dB is going to be half of the distance from AB because that line segment is going to bisect that chord. So dB is equal to 7 centimeters. Now, we also know that angle ACB is 110 degrees. And we just proved that up here that these central angles are going to create, we have these congruent triangles right here. So we know that angle A is congruent to angle B. So what we have here is this angle is 110 degrees. That means they're 180 minus 110 is 70. And that measurement has to be split up between angle A and angle B equally. So that means that angle CAD would have to be equal to 35 degrees. Now, for this other problem, it says that we're given circle P with AB is congruent to CD, so the two chords are congruent. And we want to find X. Well, what we learned about is that the two congruent chords in a circle are equidistant from the center. So we know that since these two chords are congruent, this distance from the middle and this distance from the middle are congruent. So we have 2x plus 6 equals 24. 2x equals 18. X is equal to 9. So we found the measurement, or we found the value for x. So you're going to go ahead and begin working on your homework. If you have any questions, message me on Remind or email me, or you can ask questions the next day in class.